was, but I.
Okay, so today what we're going to learn about is writing half reactions for our redox reactions that, of course, are transferring electrons from the element who loses to the one that gains. So I have two reactions here, and we're going to start them in a second, but before we do so, we're also going to predict whether or not they react or not. That's something new today. And who's talking over me? Okay.
I have not said a
Actually, it's not Liam.
It was Colin.
Okay.
Yeah,
So I have two reactions. We're going to do two reactions here, and both of these we'll write half reactions for. So the skill today is be able to, again, talking over voices. The skill today is to be able to take a redox reaction and separate, okay, separate, okay, separate who loses and who gains electrons, all right? So, if I look at these two reactants, and you have that worksheet right in front of you, I have copper and I've got tin 2 chloride. Is this a redox reaction?
Yeah.
Yes, how do you know?
Because it's a single metal.
Yeah, you're going to see a standalone metal, or you're going to see a 0. That's one quick way. Or the oxidation numbers will change, but we don't have them yet. So let's predict what's going to happen. If this is going to play out like we think, and this is called a single replacement reaction, one that you should have identified last night. This is a 0. Chlorine is -1, -2 overall, has to equal 0. This is +2, tin is +2. Most everyone navigated last night's form, being able to identify, or at least write the oxidation numbers. When something is bonded in a compound, it will have something other than a 0. So if you see a 0 and it's part of a reaction, or see a standalone element that we know is 0, why? Elements, protons always equal electrons. As we go forward, this is going to change. So if this is a single replacement reaction, what is going to replace what here? You should be able to identify what the products are. Yes, CO is going to replace SN, but don't say SN, say SN +2. Because when we're in redox, we have to be specific. If you mean copper +2 and you say copper, you've got it wrong. If you mean tin and you say tin, that's SN0. If you want tin +2, you've got to say it. So copper replaces tin +2. And it's going to go into the chemical formula. Now copper now is, I'm telling you it's going to be +2 in this case. It can be +1. And we got this. And since we kick out the tin, it'll be now SN. Yes?
Wait, why exactly do we kick out the SN?
Well, this is called a single replacement reaction. So when you have single replacement, assuming this works, copper is going to push out the tin. Now, let me explain why that works. The reason why tin +2 is hooking up with the chlorine is because tin +2 is positive, chlorine's negative. So they attract each other coulomically. Now, how in the world can I push out the tin +2? What if I make the tin +2, who's positive, who's attracted to a negative, what if I make it 0? Will it attract to the negative anymore? No, that's the key. So somehow copper made tin +2 become 0, and therefore it's not attracted. And copper became +2, and now is attracted to it. So if we do the oxidation states, chlorine's still -1. This is +2. What is the charge of tin, the standalone element? 0. So that's how a single replacement works. The only way for copper to replace tin +2, it's got to make the tin +2 become 0. How does it do that? How does tin +2 become 0? Let's talk about that for a second. I'm going to write that right here. I'm going to take out tin +2 right now. And what does it become?
0.
Right, so I'm writing half the reaction. This is redox. Someone's gaining, someone's losing. So right now, notice tin is in front of the arrow. So it stays there. Notice tin 0. Now how does tin +2 become 0?
-2.
Okay, yeah, there's a difference of a -2 somewhere. Okay? Now, where is that somewhere? Did it gain 2 electrons
Environment.
or did it lose?
It gains you.
It gained 2 negatives, right? Because 10 plus 2, when you gain 2 negatives, becomes 0. To show that in a half reaction, we put plus 2e negative. Don't get confused by the plus. That just means it's on the reactant side. That just means 10 and 2 electrons. And how do you know you did this right? Because, and this is the check, both sides of a half reaction have to have the same charge. What is -2 and a +2 equal?
0.
And this by itself is 0, you know you did this right. But the negatives make sense. If I'm +2 and I'm going to 0, I've got to gain 2 negatives. Those negatives are electrons. So what does that mean? That means electrons must have been passed to the 10 plus 2. 2 electrons. The 10 plus 2 is accepting negatives. How do I know? The electrons are in the reactant side. Okay? That, my friends, is called reduction. Now you say, my God, it's gaining electrons, we're calling it reduction. Don't forget, Leo the lion says GER. It's a nice, easy way to remember. Gaining electrons, reduction. The reason why it's reduction is the charge is going down. So how did copper make 10 plus 2 go to 0? Copper must have gave it electrons. Oh, it must have lost electrons. It must have oxidized. So let's draw copper. All right, Cu0, it's in front of the what? Arrow. I'm not changing anything. It becomes copper plus 2. Notice I'm not writing the chlorine in there. The chlorine's not changing. It's -1 to -1. And they can ask this on a test or a quiz. They could say to you, what's chlorine doing? And you would say it's neither oxidized nor reduced because its charge is not changing. Okay, how did copper become copper plus 2 so that it could track the negative chloride? Yes. How did 0 become?
You gain 2 electrons.
If it gained 2 electrons, wouldn't it become copper -2? Are electrons negative? How did copper become plus 2? How does all things that become, it lost 2 electrons. And here's the deal, if you already know something gained, the other one had to lose. If I give Brady a gift, he's got to accept it, I have to lose it. Okay? So if you're gonna lose electrons, if you're gonna lose heat, we put the electrons on the product side. And I'm putting 2 here. Why? Because it's a difference of 2. Now, what's my check? To make sure both sides of a half reaction have the same charge. A -2 and a +2 is 0, and this is 0. I don't have to keep them there, but that's my check if I make the mistake. Now, come on, party people. You have to understand, electrons have to be on one side and the other. This is called oxidation. Now, we know this from yesterday. I gave you a nice little cheat that works most of the time. The standalone metal always what? Always oxidizes. Metals that are atoms can't ever be negative. Metals lose electrons to become positive. That's what metals do. They never gain electrons. So if you see a standalone metal, you know it oxidizes. But this is the half reaction you have to identify. Okay, what substance got reduced? What substance got oxidized? Where do I pick from always? I always pick from the reactant side. The buyer and the seller in the party selling that funky candy. Okay, that's illegal.
Which one?
Okay, so let's start with who got oxidized. Who specifically lost these electrons? No.
Cu.
No.
Cl.
Essence plus 2.
No.
CuO.
Cu0.
Cu0.
Based on this reaction, it's copper 0. The standalone metal can only oxidize. Go look at your reference table. Can you find copper that becomes negative? Can you find any element that becomes negative other than nonmetals? And the answer is no. metals never become negative. So standalone metals can only oxidize. Now, was its number increasing or decreasing? It went from 0 to +2. So its number is increasing. So oxidation number increasing, hey, that is copper 0. Why is it increasing? Because it gave up its electrons. Things that oxidize always have their oxidation number increasing. Okay, now, who got reduced?
SN plus 2.
Correct, Sn plus 2. You say Sn, you're pointing me here, Sn plus 2. It's the one that accepted it. Tasa, you told me that the only way for it to get out of the tin chloride is that it has to go to 0. So you gave it electrons. And its charge is doing what? From +2 to 0. What is its charge doing? It's going down. It's decreasing. Reduction always means that the charge is decreasing. That's why they call it reduction. Your charge always goes down. Okay, notice who got oxidized, who got reduced is on the reactant side. And 98% of the time, you will see a standalone metal. That's the one who oxidizes, so it's the other element that's got an ion or positive charge that reduces. But you need to be able to identify what half reactions are. How do I know I have an oxidation half reaction? Electrons are on the product side. What's oxidation? Losing electrons. It's like exothermic. If I'm exothermic, the heat is on what side of a reaction? If I write,
Product.
right, if I put the heat here, we're producing heat, losing heat. Same thing, electrons are always on the product side for oxidation because they're losing them. And the electrons are always on the reactant side for reduction because you're gaining them, like endothermic. It's a great analogy. Always think of electrons on the reactant side for reduction, R for R. And make sure it's balanced, that mass and charge must be balanced. Okay, this is brand new. This skill right here that I'm showing you now is brand new. Please pay attention. You're going to hear the word spontaneous for the next few days. Spontaneous is a word in chemistry that does not mean that someone's going to lift you up from school today and take you to Hawaii. Okay, I know that means in human land we think of spontaneous as something happening that he didn't expect that all of a sudden happened. That's not what this is in chemistry. Spontaneity, or measuring something that's spontaneous, means does the reaction actually work? Many years before chemistry was even a science, we had people running around in the fetal age mixing chemicals. Okay, some of them figured out that it makes a big white smoke, and they'd run up to a peasant and say, "Give me your donkey or I make you disappear." And then he would hit his two hands together, make a white smoke, he'd run around it and disappear into a tree, and he'd think he disappeared. Those were the warlords and wizards back in the day. But how do they know reactions works? It was trial and error. Sometimes they mix things together, and they exploded and died. Okay, they're called alchemists. And we think of alchemy as always trying to make something into gold. Whoa, that got you. All right. But these were the early Merlins, wizards. Okay, we don't have to do that anymore. We can actually measure spontaneity. Spontaneity in chemistry just means, does the reaction occur by itself without an input of energy? Let me give you an analogy. Okay, if you're sitting in a rowboat, or let's say a kayak, who has a rowboat these days? Okay, okay, great. Okay, if you're in a kayak and you're in the Peconic River, why not? Okay, and you're going with the current. Do you have to paddle to go forward?
No.
No, because the current is taking you forward. That is called spontaneous. But if I want to paddle against the current, I only go as far as I keep what? Paddling. So spontaneous means a reaction occurs on its own. We're not forcing it to happen. Let me give you a great example. The battery that's in our phones, okay? The battery that's in our phones. Do we have a battery attached to a battery attached to a battery? No, it is spontaneous. We put chemicals together. We're going to build a battery in our next lab. Okay? We're going to put chemicals together, and they're spontaneously going to give off energy. You don't have a battery attached to a battery. Eventually, this battery does what? It dies. And then we do what with it?
Charge out.
Yeah, we add energy to charge it. Wait a minute. Have you ever had a phone charge when you pull the plug out?
No.
It only charges when the plug is. That's non-spontaneous process. Charging only occurs when you've got a constant supply. Let me give you another process. Photosynthesis, where the light energy that the plants absorb to make glucose only works when there's light out. You turn the lights out, or it's a dark day or stormy day, photosynthesis stops. Okay? All right. So we're going to do this reaction here. We're going to take copper metal. Copper 0. Here it is. Here's my copper 0.
That's SN.
That's actually SN, right. Okay, thank you. Here's my copper. All right? So copper's got this nice color. I'm going to add it, okay, to tin chloride. Tin chloride is this solution here. So we're going to put it in here and let that sit here for the...
Can you not tell the difference of the colors?
I can. That's a cloudy white and that's a blue.
No,
and
I'm
it's-
talking about the tin.
I couldn't tell from my position, but you're right. That's tin. So I'm going to put the copper, okay, metal, into the tin chloride. All right, let that sit in there. Okay? And now we're going to predict whether this is spontaneous or not, whether this reaction actually works by using something called table J. Okay, you guys have a small table J on your worksheet. And there's two parts to table J. There's metals and nonmetals. What do metals love to do?
Conduct. Give off.
Conduct electricity and give off electrons. Both are good answers. In terms of redox, metals like to reduce or oxidize. They like to oxidize. Metals that are standing alone can never gain electrons. They lose them. They're big radii. They tend to lose them. I was swinging that doll around, Elvira the outermost electron, because I wanted to show you that atoms that have electrons farther away from the nucleus can't control them. They lose them. Okay, so this is a list of metals. In this list of metals in table J, they have the metals that are the best at losing electrons. They call that most active. Metals oxidize. I've got a list of metals that oxidize really well on top. And I also have one that's really poor at the bottom. Does anybody know what the element, if you can see it on your table, that's on your worksheet, which one's dead, the last one?
Gold.
Gold, AU.
AU.
AU is terrible at losing electrons. What's that tell you? Gold doesn't oxidize. Gold doesn't rust. We think gold was the first metal found in antiquity. Antiquity means history before there was writing. No one had a written language yet. We think they discovered gold. Why? Because when you find it in the river, when you find it in its natural origin, it's shiny. It never rusts. Almost all the metals we find that we mine for are oxides or ores, which means they've already rusted. They've given up electrons and bound with oxygen, and we have to do the opposite to clean them up. Gold stays shiny. That's why it's something that's revered forever. Also, we use it for electrical contacts. Important electrical contacts that we do not want to oxidize and break down are made of gold. Okay, gold resists oxidation. It doesn't lose electrons. But then we have these other metals up here that are very reactive. And the higher you go, the greater the ability to oxidize. Some of these when you drop in water, and by the way, didn't I show you the videos of me dropping some things in water? And as you got bigger, they were more explosive. Remember that? Okay, well, any case, as you go up, you're better at losing electrons, you're better at oxidizing. Okay, how do you use this chart? Very simple. If I've got a reaction between two metals, if this is spontaneous, wouldn't it make sense the one who can lose electrons better should? If this reaction, hello, hey, wake up, off your phone, stop. How can I teach this to you? I'm saying that if this reaction works, copper's got to oxidize and tin plus 2 has to receive. That only works spontaneously if copper is the one who's better at losing electrons. So how do I do that? Go find this list and go find copper. Circle it. I know it's tiny, but it's right here in my little chart right here.
Third to last.
Actually, that's right. I can't see. That's calcium. Copper is here. Thank you. So copper doesn't like to oxidize. Hey, that's why they use it for copper pipes in your basement. They don't use reactive metals. Now, you can't afford gold. Maybe you can, okay? But I know I can't. So copper is pretty expensive metal because it risks oxidation. We do not want our metals to corrode. So we have PVC and we have copper pipes. Now, so copper is terrible at oxidizing. Is tin above it? Is SN above it? Yes, it is.
Yeah, 2 above.
2 above. So this is tin. So this is not going to be spontaneous. Not. Or I'm just going to put X here. Okay? It is not spontaneous. Because the metal who's better at oxidizing, which would be tin, is actually getting reduced. So what we're saying is copper isn't good enough of pushing its electrons onto tin. So this is not going to work. And this reaction, even though I did all this work here, doesn't actually occur. Okay, that's important you understand that. How did I do that again? I found the one who oxidizes. I find my metal side. If this is spontaneous, the one who's oxidizing better be higher than the one who's what? Reducing. In this case, was over tin. And because copper was below tin, copper's weaker than tin in giving off electrons. So copper is not strong enough to push electrons onto tin. Now you say to myself, well, wait a minute. Tin is +2. It's reducing. How do I figure that out? The one who's oxidizing is higher. The one who's reducing is lower. But the way to think about this too is if tin is better at oxidizing, isn't it worse at reducing? Right?
Yep.
If tin is better at gaining, it's worse at accepting. So we've got a chemical who's bad at accepting and who's bad at what? Giving them off. This doesn't work. If you don't like my explanation, the one who oxidizes has to be higher than the one who reduces. This is not the case. This doesn't work. Okay? Let's go on to the next one. Okay? Now, can we all see it from here? Okay. How do we write this reaction? We're going a little faster now. What are the products here of this single replacement reaction, which is an example of a redox reaction? Tin is going to kick out the copper. What are we going to make? SnCl2. And if copper gets kicked out, it's just going to be plus Cu. And when you say Cu, it's 0. Hey, where's my zeros at?
On the
Sn.
And
Chlorine's -1, -1. Tin is +2 for the same reasons above, +2. We should be able to do that. Okay. Now, I'm going to do this reaction while we're waiting. I'm going to put tin into copper chloride. Copper chloride is that blue-green solution. So here's my tin. Tin is a pretty metal. Okay? I'm going to put that here. Let that sit there. Okay. Now, we'll get back to that and see if it actually works. Let's do the half reactions. I'm going to pull out tin. It's on the left side. It stays there. I'm going to pull out tin +2. I'm not changing its positions. I'm just pulling out half the reaction. Someone's gaining, someone's losing. Why did I pick out tin? Because I see its numbers are changing. Why am I not pulling out the chlorine? Its numbers are not changing. It's not oxidizing nor reducing. Okay, how did tin 0 become tin +2?
lose 2.
It lost 2 electrons. So if I'm going to lose 2, I put the 2 electrons here. But I check. A -2 and a +2 equals what?
0.
And this is 0. I know I did it right. Here's my mistake. This is not correct. If I put it over here, a -2 and a 0 is what?
-2.
And that side's +2. Charges must balance. So we put the 2 electrons over here. Okay. Next one that changes. Copper +2 is on the reactant side. Notice I'm leaving chlorine alone. I'm pulling out the copper +2. I only care about who is accepting or losing. And then it goes to copper 0. How does copper +2 become copper 0? Is it gaining 2
Gaining
negatives?
2.
It's gaining. And if I'm gaining something, I put that on the reactant side. Okay. And I check. -2 and a +2 is 0. This side is 0. They're not always going to be 0, but but they're always, if you do them right, gonna have the same charge. Now, who specifically got reduced? And if you forget,
Oh,
Leo
second
the
one.
lion says
The first
Gerd.
one. Second one.
The first one is producing electrons. And by the way, metals standalone can't reduce. They can only oxidize. Remember yesterday, this must oxidize. So copper plus 2 got reduced.
I would feel it to be so
Who got oxidized?
The first one.
Well, who's the first one?
GN.
SN. SN got oxidized.
Because it's a standalone.
Right, standalone metal. Okay, whose oxidation number is increasing?
SN.
SN. And that's another sign it's oxidizing. Who is decreasing? Cu plus 2.
Will they always be on opposite lines if it's set up like this?
Yes. The one who oxidizes will always have an increase in charge because it's losing negatives. The one who reduces will always have a decrease. Okay. Now, is this a spontaneous reaction? Who's oxidizing? Is tin above copper?
Yes.
Yes. So the one who's oxidizing is strong enough to oxidize, so it can push its electrons onto the copper plus 2. This is spontaneous. Get a check mark here. And all I got to do is take the one who's oxidizing and see it's above the metal who's reducing. Yes. Okay, no. All right. So, the question is, the first reaction, did it work? According to table J. The first reaction where I put what? I put copper into tin chloride. And we're saying that it didn't work because copper was below chloride in table J. So let's take a look at this reaction. Anything happen? No. I mean, it's cloudy white, but nothing's there.
No, it did get a little bit
On the actual
lighter.
metal, it did.
It might have actually got a little cleaner.
Yeah. it
But
does.
let me show you. But that could be a side reaction. But in any case, let's take out this one. This one was spontaneous. What does spontaneity mean? The reaction.
Spontaneity?
What does spontaneity mean? Or spontaneous? I think you were in the
Like not likely to happen, or like I don't
It's
know.
not
It's a measure where the reaction occurs. Was this spontaneous?
Never mind.
No.
I'm gonna stop.
Yeah.
Yes. Copper. I'm sorry. Tin was higher than copper, so that means tin was strong enough to force the electrons on. So this reaction, based on what we found, works. So this one should have what? A reaction.
Oh yeah.
What?
Now,
Rainbow.
for those that can't see,
It's rusted.
can you guys stop banging on the table?
Column.
Okay, I know it's hard to see, but
Stop.
there's actually something on this tin. It looks brown, right?
It's rust.
Okay, it's not rust. Look at the reaction. Tin gave its electrons at copper plus 2. Copper plus 2 became what? 0. Moved out. Tin plus 2 moved in. What we have here, guys, is pure copper that's on here.
What was it before?
It
Oh,
was
you
in
never,
the
like, rub that
solution.
off?
It was in the solution. If you blow it up, copper plus 2 in the solution, floating around, hits the what? The tin metal. Here's what happens. When the copper hits the tin metal, because tin is good at what? Oxidizing, or stronger than copper oxidizing, it gave electrons to what? Copper plus 2. And it became what? Copper 0, which is the solid form of copper. Anytime copper or metals are 0, it's the solid form. Okay? So for those that can't see, you should be able to see that we have a buildup of copper on the shiny tin. Okay? I don't know if you can see that there. Okay? But you can see the shiny tin on top. Okay? All right. Okay, now, let's continue this worksheet. All right? So, let's get rid of this. Let's go to the bottom. Okay? Can tin replace iron in iron chloride? Think about what we just talked about. These are all Regents questions, by the way.
Yes.
No,
No.
no, because it's lower.
Oh, where is that?
So the question is, who's going to oxidize here? The standalone what?
Metal.
Metal. So is tin, Sn, higher than, now iron in iron chloride is F plus 2. Is tin higher than iron?
On table J?
On table J.
No.
No, it's not. So tin is not strong enough to push the electrons, and this would be no. Not spontaneous. It doesn't work. How about this? Can tin replace gold in gold chloride? Now this is gold plus 3.
Yeah.
Is tin higher than the gold ion?
Yeah.
Yes. Tin is higher than gold. It's that simple. This is spontaneous. Spontaneous means it works. Let's go on to the backside. These are all Regents questions. Okay? Okay, we're going to skip 5 because, no, it's, we'll do 5. And we'll go up to number 3. Okay, here we go. Okay, we can move a little faster now. You can guess what your homework's going to be on, writing half reactions and figuring out if reactions are spontaneous. Okay, here we go. We have copper plus hydrochloric acid. Okay, here we go. So we're going to replace the copper with the H. Single replacement. I'm going to tell you copper is plus 2, so we need 2 chlorides. And then we're going to kick out the H. Is H a Hofbrinkel? Is it diatomic? Yes. So I got to write H2. Not really worried about balancing. We'll get that another day. But that's the 2 products here. Okay? I guess we could balance by throwing a 2 here, right? Now, half reactions. I'm going to start with the what? The standalone what? Metal.
Metal.
So copper 0 becomes what? What's its charge in here?
-2.
-1.
Metals can never be
Oh, plus
negative.
1.
Plus 2.
Plus 2. -1 apiece, -2 overall, has to equal 0, plus 2, plus 2. Okay, and where do electrons go so that both sides of a half reaction have the same charge?
On the product.
Correct, because a -2 and a plus 2 gives me 0. Now this is -1. Hydrogen, like last night, is always plus 1, except when it's bonded to an alkali, earth. So here comes H plus. And what does H plus become? What is the charge on H2? It's a standalone element.
H0.
0. I'm going to write H2, and I put a 0 here. Now, there are 2 H's bonded, so I'm going to throw a 2 here. Right? There's 2 H's bonded, so I'm doing 2 H pluses. How many electrons do I need, and where do they go, so that both sides of a half reaction have the same charge?
On the reactants.
Has to, because I'm losing. Now, one of these becomes 0 by gaining an electron, but there's 2 of them. So there's 2 electrons. Okay, who got reduced? Who is gaining electrons? Who is Goering?
H.
H what? 0 or H plus?
Plus.
You always pick from the reactant side. Okay, its oxidation number is what? It's going from +1 to 0.
Went down.
Yes, it's decreasing. Why? Because reduction means your charge goes down. Who's getting oxidized? The standalone metal. And its charge is going what? Increasing. Is this spontaneous? Can copper with hydrochloric acid make hydrogen gas? Okay, I go find copper. It's right here. I gotta find hydrogen. Now we really should be looking for H plus, but they put H2. Where is H2 on this chart?
Right above it.
Right. So is copper better than oxidizing than hydrogen?
No.
No, so does this work?
No.
No, this is not spontaneous. I can't make hydrogen gas. That means this, party people. If your water gets acidic, it won't dissolve the copper in your pipes. That's why we use copper. Would gold be better?
Yeah.
But why don't we use gold?
It's too expensive.
Right, and the heaviness would fall out of your sinks, okay? So back to this. Which of the following replaces tin in tin chloride? Okay, tin chloride. If this is +2, it's going to reduce, correct? The element that's bonded to the chlorine that's positive must reduce. So what am I really asking you? Who is above? Party people, if you knew nothing, because you're on your phone again, pick the one that's different. There must be what? 1 above and 3 below. Yes?
What if there's 2 above?
Then I made a mistake.
TI and PB.
Okay? Which of the following replaces tin and tin chloride? Tin must what? Reduce. So who's above tin?
TI and PB.
I think PB's below it.
Oh, yeah, no, never mind.
Yes, so titanium's the only one above. Look at this. This is exactly the same question. Party people, focus. We're almost done here. Which of the following can reduce strontium ions? That's the same thing as saying this. I'm looking for something that's been oxidized. Who is what? Which one is, if this is reducing, I'm looking for something to be what?
CS, higher.
Yes, cesium. And last but not least, and we're done today, which metal will react with hydrochloric acid to produce hydrogen gas? Uh-oh, same kind of question. So we're talking about H plus is reducing. Don't stand up, don't pass go, I'm not done yet. Oh! Who is higher than hydrogen?
CN.
Zinc.
We just did that
We did it sort of.
before.
Okay, oh, by the way, when I made hydrogen gas in the balloons to explode, or at least in the Pringles can, I used zinc and hydrochloric acid. Have a great day. Can you hit stop on that for me?
Good to know.